Professor Anna Motiti, Executive Dean, Faculty of Science, Professor Rajendra Pant, inductee, Professor Mujahid Abbas, Department of Mechanical Engineering Science at the University of Johannesburg, members of Senate and other academics, distinguished guests, students, all who have joined us online, Sanbonani, Khoyenant, good evening, Tobel. It is indeed a great honor and a special privilege for me to welcome you to the Professorial Inaugural Lecture of Professor Rajendra Pant. As I do so, I wish to express a warm welcome to his loved ones, special guests, and colleagues. This is indeed a proud and joyful moment, and it is also a landmark moment for all of you, for Professor Pant, for us here at UJ, for higher education in South Africa and beyond. This is particularly noteworthy as we celebrate 20 years of UJ this year. Since the merger in 2005, we have come to exemplify how excellence and access are not mutually exclusive in higher education. In the spirit of innovation and social responsibility, UJ has pushed boundaries and prioritized research, technological advancement, and community engagement. It is against this backdrop that we welcome you into the Professoriate, a community of scholars dedicated to UJ's ethos of academic excellence while making a tangible impact on society. The inauguration of professors is a public ceremony in which newly appointed professors are inducted into office by the Vice Chancellor and deliver their inaugural addresses. The ceremony has its roots in the medieval university and serves multiple purposes. First, it is an expression of welcome and an entry for new professors joining the circle of colleagues who are already professors. Secondly, it provides a platform for professors to display their expertise in the discipline and showcase their research. In the colonial traditions subscribed to by many universities, assuming the role of the professor refers to the gown and the cap. Once we have listened to the inaugural address, the gown denoting the professorship will formally be assumed. Today, we gather to witness Professor Rajendra Pant's entry into the illustrious community of scholars at our university. We celebrate his contributions to the discipline and ultimately his impact on society. Professors provide a university with its identity, character, academic legitimacy, and integrity. The inaugural lecture is a rite of passage following the confirmation of the appointment of a person as a professor. This evening, we will listen to Professor Rajendra Pant as the gown goes to town. By this, I mean that the power of the inaugural address is when the expertise is showcased beyond the corridors of the university and reverberates with society. It stands out as a moment of pride for the incumbent, the family, fellow scholars, the university, and ultimately society. In the past, several philosophers and scholars have defined universities using very narrow conceptualizations. For example, the search for truth, for universal knowledge, and even as instruments serving the purpose of the economy or being utilitarian in nature. Through our work and research at UJ, I hope that we can break out these narrow conceptualizations and reflect on the university as contributing to the public good, working towards societal impact, driving Strategic Plan 2035. What is the role then of the intellectual? Edward Said, in one of his articles, defines the role of the intellectual as one who commands a vast knowledge of a specific discipline, one who is rigorous in the analysis of literature, one who views being an intellectual as a vocation, and one who functions as a kind of public memory to recall what is forgotten or ignored, to make the connections that are otherwise hidden, and to provide alternatives for mistaken policies. Wow. It remains then for us as a university with a Pan-African vision to derive our mandate as intellectuals and as professors. And importantly, how do we embrace the role of a professor as a disruptor while continuing to be flagship careers of our disciplines? This evening, we will listen attentively to Professor Rajendra Pant as one further step in the journey of being a professor. This is a journey which does not conclude once this lecture has been given. Notwithstanding, this inaugural lecture does create an opportunity for a self-reflective pause in the journey of the professor. Let me now invite the Executive Dean, Professor Anna Motete, to introduce Professor Rajendra Pant. I thank you. Ke a leboga, ngiyabonga, bayadanki.
Vice-Chancellor Functionary, Professor Paswana Mafuya. Please allow me to observe protocol. I know we're not allowed to do that, but I'm lazy tonight. Good evening. Good evening. It is a good evening. Like a true mathematician, Professor Pant has kept his bio to the minimum, short and sweet. And I will read it. It reads as follows. Professor Rajendra Pant obtained his master's degree in mathematics from H&B Gawal University, India in 2002, and his PhD in mathematics from Gurukula Gangri University, India in 2008. I'm sure I've butchered those names. Professor Pant began his academic career at SPRC Postgraduate College in India in 2002. He has since held academic positions at several universities, including Walter Sisulu University and the Visvesvaraya National Institute of Technology, one of India's leading technical institutions. He joined the University of Johannesburg in 2018 as an associate professor and was promoted to full professor in 2024. An active researcher in fixed point theory, topology, and nonlinear analysis, Professor Pant has published more than 70 peer-reviewed journal articles, authored several book chapters, and edited the volume Recent Advances in Fixed Point Theory and Applications. He serves on the editorial boards of Fixed Point Theory, Applied General Topology, and Advances in Theory of Nonlinear Analysis and its Applications, and regularly reviews for prominent international journals in analysis and topology. Professor Pant has supervised 5 PhD students, 11 master students, and has hosted 3 postdoctoral research fellows. His research collaborations span institutions in Romania, India, Serbia, Spain, and South Africa. And he has delivered invited and keynote lectures at numerous international conferences. He has received research funding from the NRF, the Center of Excellence in Mathematics and Statistical Sciences, and also internally from the University of Johannesburg. He currently holds an NRF C2 rating, having previously been rated Y2. In addition to his research achievements, Professor Pant has contributed extensively to academic leadership through departmental administration, curriculum development, moderation, conference organization, and community engagement initiatives, advancing both teaching and research within the mathematical sciences. Ladies and gentlemen, I give you Professor Rajendra Pant.
Thank you. Honorable Professor Mafuya, the Vice Chancellor's representative here, and our Deputy Vice Chancellor Research, Professor Motiti, the Executive Dean of Faculty of Science, Professor Abbas, my respondent, Professor Nebaja, the head of the Department of Mathematics, fellow colleagues from the Department of Mathematics and Applied Mathematics, family and friends, media people, a very good evening. I will do acknowledgement at the end, and this has been the trend set by our HOD in his inaugural lecture, so I will be following him. Today I will be talking about my research, and the title of my presentation here is Approximating Solutions of Nonlinear Functional Equations in Infinite Dimensional Spaces. Let me dedicate this talk to two heroes of my life. One is my father, and another is my supervisor, PhD supervisor. My father wanted me to do PhD in mathematics, and the man who made it possible was Professor S.L. Singh. Unfortunately, they both are not in this world, but wherever they are, I hope they will be happy for me today. The outline of my talk is going to start with I would like to motivate non-mathematicians and even mathematicians to watch at least these two movies, which I'm going to present the titles of the movies, and then you will find that how much struggle in the mathematician's life is there. And then you will find that the happy ending in these movies. Let me start with the man who knew infinity. It is a movie about Sir Srinivas Ramanujan. He comes from number theory, and as we know that whenever we talk about mathematics, the number comes first. So that's why I wanted to highlight this. In this movie, a struggle of his life is shown, and then it is shown that even though he was struggling, but how he contributed, and it is believed that he proposed 4,000 conjectures in his life. Proposing one is a real conjecture in mathematician's life is very difficult, but he did so. Another story is the beautiful mind, and this story also tells that how much struggle can one have in his life, but still one can achieve. So these two movies one can watch and see that how difficult it is for mathematicians to really develop methods. Let me go to the content, and let me explain that what basically we do. So I'm a fixed point theorist, and let me give you a definition in the layman's language. Suppose you are standing in front of a mirror. When you raise your hand, right hand, then you will see that the left hand is coming in the mirror. So there is a movement. But if you are standing straight in front of the mirror, your nose stays where it is. So it means by the mirror rule, it is not changing. So that is called, we can treat it as a fixed point. Then, nowadays we do selfies. I hope everybody does it. So let's say in a selfie, we would like to make ourselves, if we are women, then beautiful, men handsome. So for that, we apply sometimes filters also. So let's say a filter does the photo smooth. If the photo is rough, then it will do smooth, so it will make a change. But if the photo is already very smooth, then it is not going to make any change. So it means that is the fixed point. Let me take some elementary examples in mathematics on real line. So I have a function here which is tx equal x square on the interval 0, 1. And even the non-mathematicians can see that if I put 0 in the left, the right-hand side is also 0, because the square of a 0 is 0. And if I put 1, then the square of 1 is also 1. So map is not making any change on 0 and 1, but other numbers will get changed, one can check. Similarly, if I have tx equal 1 minus x, and if I take x equal 1 by 2, then the left and right is the same. So there is no transformation happening. But if I take tx equal 1 plus x, then there is no number x which is going to be equal to 1 plus x. So here I have tried to explain three situations where I can have more fixed points. Like in the first case, I have 2 fixed points. In the second case, I have only 1 fixed point, 1 by 2. And there is a condition, there is a mapping where there is no fixed point. So we can have some kind of transformations where we have fixed points, where no fixed points, where multiple fixed points. But why these fixed points are important, I will come to that. The formal definition here is that, let's say we have a set of points. I hope everybody understands. And then if I have 2 set of points, a transformation or mapping is a relation between these 2 sets with certain rules. And if we define that relation, under that relation, if I define a transformation like I did in the previous 2 slides, a point P is said to be a fixed point of that transformation or the mapping if it doesn't change or it remains invariant under that transformation. The study of fixed point is concerned about the condition under which we would like to ensure that the fixed point exists, either unique or multiple. But why? Actually, in a number of problems, the fixed point of some suitable operator is actually the solution of the problem. So that's why we are interested to study this. Therefore, the existence of fixed points is an important area. In fact, this in the nonlinear analysis, possibly this is the only tool to study the existence of solutions. So broadly in mathematics, there are 2 types of problems. One, we would like to know whether a system or a problem does have a solution or not. That's the first problem. And the second problem is that if there exists a solution, how to obtain that solution. And the fixed point theory does both the things. So it gives you the existence theory as well as the second part we call as the convergence theory. Here, there are many areas where we can easily see the fixed point theory can be applied. I'm going to present 2 applications to motivate that, yes, it is something which is useful. Let me start with the Nash equilibrium. I have just highlighted the film, The Beautiful Minds. Why these minds are beautiful, let's see. Actually, in the game theory, the Nash equilibrium is a situation where which no player can gain any advantage by unilaterally changing their strategies, provided that the other player keeps his strategies as the same. This is a the mathematical model for it, that we make a set of strategies of both the players and then a mapping on that set, and then the equilibrium will be obtained where the fixed point of this map achieves the fixed points. And which theorems I will come in the details later. So Brau's and Kakutani's theorem, they guarantee the existence of such fixed points for these type of problems. What is happening actually? I'm going to consider a 2-player game. So let's start with a game so that everybody enjoys. So we have a 2-player game and both the players have some payoffs, and they will try to make, because whenever we are playing, then we are trying to make our best responses by to the other player, looking at their strategies. And wherever this intersects, then that will be the equilibrium point. So let me take an example here. So this is the game is called, this is a classical game which is called as Battle of Sexes. And here we are going to discuss the Nash equilibrium. So there is a couple, so they want to spend the evening together, but then their preferences to watch games is different. So the player 1 prefers to attending opera, and the player 2 would like to attend the football. So let's say the women want to go for opera, and the man wants to go to football. Now, but then their preference is like that, they want to go at one place, not separately, because they want to spend that evening together. So we have formalized a game here. So let's say this is the table with which we have the pair of red colors for the player 1, and the blue colors are for the pair for the second player. So what is going to happen? Actually, if there are 2 types of Nash equilibriums, one is called with the pure strategies, and then one is called as the mixed strategies. The pure strategies that if you know that what the second player can happen, then you can plan your. If the second player randomizes its choice, then how you are going to get it. So let's do the mixed one because it's a little bit tricky thing. So let's say the first player would like to play U. U means the opera with the probability P, and the player L goes with the Q. So because there are only two choices, and the sum of the probabilities will be 1, so if it is going for P, then the second choice will be 1 minus P, and the vice versa. If he goes for Q, then it will be 1 minus Q, because the total sum is going to remain as P and Q, the 1. Now, the expected payoff from this table, so what will happen actually, the first player will go with the row. So if he goes for U, and let's say the second player also goes with the opera, then the first player gets the payoff 2. And then if he goes for the opera, but the second player goes for the football, then he gets 0. So from that point that we have calculated 2Q plus 0 minus 1Q, and that is going to be 2Q. And the same way, if the first player goes for the football, then this is going to be 0 times because the probability of the second player, the strategies of the first player will depend on the strategies of the second player. And his probability of choosing these things is Q, and 1 minus Q. So that's why it will be again playing the football will be like this. And because in one move you can go once, so there will be indifference between these two things. So we have sorted the Q will be 1 by 3 by equating these two quantities, and we solved it. It's a straightforward. Similarly, the player 2 goes with the strategies of the first player, whose probability of switching these things will be P, and that the same way we have formulated them with these one, and then we got the value of P. So in this case, we got the P star and Q star, those are the solved values, and this is the Nash equilibrium for the problem. Why this equilibrium problem is important? Actually, John Nash was a mathematician, but mathematicians are unfortunate to get the Nobel Prize, but he solved this problem in economics, and then he shared the Nobel Prize with 2 other economists. Also, the conclusion of this equilibrium problem is that the supply and demand, when they meet at one point, that is called as the equilibrium point. And when the supply and demand they meet, then the economy is healthy. If the demand is more or the supply is more, then it is not a balanced economy. So that's what is the conclusion of his theorem. Now, let me take another problem, which can also be solved as the fixed point problem. That let's consider the steady heat equation in physics. Consider a thin metal plate occupying the boundary region, and we have the sigma in the R square. So I have a thin plate, square plate, or the circular plate, depending on what type of problem you are dealing with. We want to find the steady state temperature distribution on the plate. So because it's a thin plate, so we are considering that there is not too much thickness, so it means the temperature on the top side and the bottom side remain the same. Now, this problem can be formulated using the Green function like this integral equation. Though it's a Laplace equation, it's a differential equation, but we can convert it into an integral equation. And then we can write it as an operator equation, because I'm saying the functional equation. So functional equation means now we are trying to write the equation in terms of the operators, and then the fixed point of the operator is the solution of the problem. So this is basically means the solution of the problem can be guaranteed if this operator has a fixed point. And which theorem we can apply here? That is the Schauder's theorem that guarantees. So the key idea here is that the physical stability and the equilibrium often correspond to the fixed point of the evolution operators. Now, let me go where this theory begins, how the theory started. Actually, people were doing successive approximations in 1700 and 1800 centuries, but then this was formally started by, the theory was started by the result of Dutch mathematician, de Brouwer. So what he said, he gave a very simple but very powerful theorem. So it says that a continuous mapping on a closed unit ball in Rn has a fixed point. The one-dimensional solution, the proof of the theorem is very straightforward. It comes from the intermediate value theorem, which we usually teach in undergraduate courses. But when we go in the second dimension or the higher dimension, the proof becomes very difficult, and we need the algebraic topology to apply. This marks the beginning of the So in the some problems in analysis, particularly in PDE and other areas, the infinite dimensional spaces are needed, so Brauer's result cannot be applied. Then another mathematician called Schauder in 1930 obtained the infinite dimensional version of this theorem, and he proved that let C be a non-empty convex compact subset of a Banach space. If T is a continuous mapping, then there exists at least one fixed point for this mapping. Then other than that, also actually what happens sometime, both the theorems are single valued. Single valued means actually, let's consider a machine. So some machines, they give you only single output. You put some input and then they give. But sometimes you can have multiple outputs from the same system. So similarly, under some transformations, actually they don't give you the single point, but corresponding to one point, they give you a transformation as the set. These mappings are called as multivalued mappings. And they are also, in fact, the Nash equilibrium problem I considered was single valued here, but in most of the situations you get the multi-valued outcomes if you are dealing with a bigger game. So then how you can apply that one? For that, Kakutani obtained in 1941 a generalization of the Brauer's theorem for the set valued mapping. So here we have K, a subset of Rn, and which is compact and convex, and T is a set valued mapping. So that's why I'm using two arrows here. So it is mapping for a point to the set, and that Tx is basically a set corresponding to each point, and that set, if it is non-empty, compact and closed, non-empty, convex and closed, and T is hemi-continuous, it is some kind of continuity, then there exists a point which belongs to the set, and that is called as the set valued fixed point for T. Now, what basically I do? Another powerful result was obtained by Polish mathematician Banach in 1922. This says that every contraction mapping T on a complete metric space XT has a unique fixed point. Actually, metric space means we have a set of points and we have equate with some distance function. And there is some kind of completeness. So for technical reasons, I'm not going in that details. So contraction means the mapping is bringing the points closer. So distance between the images is becoming less than the distance between the points in the domain. And this then, it guarantees the unique fixed point for the mapping. This line of research, which is well known for its constructive way of proofs and tremendous applications, is called as the metric fixed point theory, and this is where I work. Actually, we can see that how important this theorem is. If we would like to go and study the existence of the differential equations or integral equations or the system of linear equations, this is the only tool you can apply to ensure the guarantee of existence of a solution if the system is formulated as the operator equation, and if the operator is a Banach contraction, then you can guarantee the unique solution of the system. We can also see that how powerful this result. In 2004, 3 mathematicians wrote this quote for the Banach contraction. If the works and achievements of mathematicians could be patented, then the contraction mapping principle would probably be among those highest earning up to now and the future. So this result is very powerful. Now, once we know the Banach contraction principle, actually there are two problems with the theorem. Means not problems, means if we would like to consider the discontinuous mapping, because the contraction condition does force the map to be continuous, plus the converse of the theorem is also not true. So these are the two shortcomings with the Banach contraction theorem. Then in 1974, a Serbian mathematician extended Banach contraction theorem to a more general setting, and there the continuity is no more required. And this, one can understand that this paper has been published in Proceeding American Mathematical Society. So this result says that if we have the same setup, the only thing is that we are just changing the contraction condition. Instead of having the distance between the points, we are having all, because we have the x and y, here we are taking the distance of x and y with tx, ty all. So if the maximum distance is taken, is still the outcome of the Banach contraction theorem remains true. and then the continuity condition is no more required. So one assumption has been waived off from the theorem, and there is the class of mapping going to satisfy this condition is a wider class of mapping than what the contraction conditions are there. In fact, in 77, a American mathematician compared all type of contraction conditions studied by that time, and he noticed that this theorem is the best result obtained by the CIRIC. Then, actually, in all the theorems I presented till now, the contraction condition or the continuity conditions or any other condition needs to be satisfied on all points of the domain. So is there any possibility not to check on all the points but on the certain points in the domain? A Japanese mathematician made a significant beginning in this direction in 2007, and the paper is also published in the same journal where these two papers were published. And he said that, okay, we don't need to check the contractive condition on all points, only on those points where this precondition is being satisfied, and if still this happens, then the conclusion of the Banach contraction principle will be satisfied. The advantage of this theorem is in two ways. Actually, first is that it is a generalization of the Banach contraction theorem, plus the continuity is not required because we are not considering all points. And additionally, it does if every Suzuki contraction has a fixed point on the metric space, then metric space will be complete, which is not in the case of the Banach contraction principle, because the converse is not true. Now, what we did, actually, we looked at when I started my journey in this theory, then I was motivated by these two results. That one is the Suzuki obtained when I just about to finish my PhD. Then this result came in 2007. I completed my PhD in 2008, and then I was very impressed with this result. And plus the other result, which was CIRIC obtained in 1974. So then what we did, actually we tried to find whether there is a class which can contain both of these classes and still the outcome remains same. We could do it for some particular theta 1 minus r, and the problem with the general theta r is still open, and we did prove that yes, we can obtain the same conclusion as these theorems gives. Then let me go to iterated function systems. Actually, in nature, when we look at, then you will see the everything cannot be represented in Euclidean geometry, means the dimensions cannot be 0, 1, 2, and 3. Let's say if you are at a river course, so how do you measure the dimension? It's not cylindrical, it's not going to be plane, it's not going to be, so such type of objects comes under the dimension we call as the fractal dimension. And in nature is full of the fractional dimensions. Even the tree, if you look at, so you will find that every tree has its own type of shape, and you cannot fit it in the Euclidean geometry. Also, then another thing, in the nature you will see, let's say if you in some of the trees, the branches, when you go on each branch and you cut, then they look like the similar. If you look at the leaves also, fine. So that's called some kind of self-similarity. So in the fractal geometry, we study this type of problems where we do have self-similarity and where the dimension is not the integer dimension, but the fractional dimension. So using the Banach fixed point theorem, Hutchinson and Barnsley developed a theory which is called now HP theory, and they studied iterated function systems. Here what happens, because they started with the contraction mapping, so they considered a class of contractions with different contraction constants, and they defined the operator this way, where the kx is going to be the set of all non-empty compact subsets of x, and they defined this operator which is going to be the union of the fn applied on that set. And then they obtain some results. Now let me show you that what is basically happening, how mathematicians are getting inspired by the pictures in the nature. So you see we have a line here. If I pull the middle point of these 2 points, then I will get this shape. And if I continue doing these things, then you will be generating this type of curve. So you have reached to the middle point, then again you have the dot here, then you pull it. So this way you can generate the curve, and that is called as the Koch curve. But how difficult it is, you can see the mathematical formulation is not going to be so simple. So we have the contraction mappings here to generate the curves, which seems to be easy in the drawing, but when we come to plot it by the equations, then you see here. Another shape I'm taking here is the, here I have a triangle, so I'm just joining the middle point of the triangle. Means each side I have gone in the midpoint, and I created 3 dots on the 3 sides of this triangle, and I joined. And I continuously doing them and giving different colors so that visibility is good for us. And then we generated this, this plot here. So this is called as the Sierpinski gasket. So one can see that if I cut the piece, it will look like the original one. So it is something called as the self-similarity. Now what we did, this picture can be generated by these 3 contraction mappings. And what we did in 2024, me and my co-author obtained a result which is a more general class of contraction, and we try to understand whether this class can also be applied to the fractal theory as or not. So we obtained this result where we have a complete metric space and the operator defined this way. Then this we ensured the existence of the fixed point, and then we would like to validate whether this is going to satisfy some criteria or not, and then we generated this image. Now, from the contraction theory, let's go to the non-expansive. So if we remove the k equal 1, if we replace the k equal 1, then the class we considered with the Banach contraction becomes the non-expansive mapping. But as soon as you replace k equal 1, the existence of the fixed point for these mappings cannot be guaranteed unless you enrich the space with geometrically rich. Actually, what is basically happening whenever we are studying fixed point theory, so there are two things. One is the space in which you are studying this theory, another is the operator which you are considering. So if you have fixed the operator that it has to be non-expansive, then only you can play with the space. Which geometric conditions are needed? So let me start with the geometry. Actually, in this case, we need to have the normed spaces. Normed spaces means you can say that you are in a world where you can have objects, you can measure their size, allow them to talk, distance, limits, all those things which you can't do in the metric space settings. Now, here let me describe 3 norms on a simple space which is R squared. So I am in a plane where I can define the norms by these 3 rules. So we have 1, 2, and infinity norm. And if I generate the unique ball, because you see whenever we are talking about the radius and the circles, then you will always think of a circular thing. But with the different distance function, the unit circle need not be a circular type of shape. It can be a diamond, or it can be a rectangular or the square shape. So here I have generated. Now, basically we would like to understand that what is the midpoint theory here. So in the midpoint, you can see if I join the point, if I have 2 points on the boundary, and if I join a line, the point sitting on the boundary. But when I come on the circular shape, the point falls inside the boundary. And this type of shapes are called as the strictly convex sets. And in the finite, if we have the strict convexity in the finite dimension, then it implies to the uniformly convexity, which I am going to use here. So uniform convexity means the shape is equally rounded everywhere, and there is no place where the boundary becomes almost flat. The second geometric property I need here is the diametral point, or I am going to use the diametral means the points are far away. A space has normal structure if every reasonable shape inside has the some point that is the farthest. Why we need these, actually, let me not go in the technical definition. So let me tell you, actually what happened, the Banach contraction principle came in 1922. But it took mathematicians almost 43 years to generalize the theorem to when k is replaced with 1. And 3 mathematicians, they came together, Browder, Gode, and Kirk, and they obtained two different, two mathematicians, Browder and Gode, proved the same result. They proved this existence result for non-expansive type mappings in uniformly convex Banach spaces, while Kirk obtained the same result in the same year with slight different setting in the normal structure, the Banach spaces. These are the results for them. Now, as we also, as I am the metric fixed point theorist, so I also looked at, because these are the well celebrated results in fixed point theory, so I started working. And in these two cases, what is happening, because the non-expansiveness is again forcing the map to be continuous, so can we have the same result for the discontinuous mapping? So we generalized these mappings to a new class of mappings where the non-expansiveness need not to be satisfied on all points in the domain, but certain points on the domain. This idea was motivated by, again, the Japanese mathematician Suzuki, and then we defined this class, and we obtained a result in 2017 that if K is a bounded closed convex subset of uniformly Banach space and T is the mapping which we defined, then we can ensure the existence of fixed point provided it has an approximate fixed point sequence. Very recently, me and one of our PDRF at UJ, we did look at the result, and we found that the additional assumption of having the requirement of approximate fixed point sequence is no more needed. The result can be proved as it is, and then it becomes the generalization of the result of Kirk, which is the more general case of the Browder and Gode. So this result has just come out in 2025, just before my inaugural. Now, let me take you that where we are and what are the future problems. Actually, in fixed point theory, there are some open problems, and I have started working on these problems soon after joining the UJ in 2018, because I started studying these mappings in 2017, and we are working on these problems. What is the problem? As I said, that once you have fixed that the class of mapping you are going to study this one, then you can only play with the space. So a normed space is said to have fixed point property for a class of mapping if every, means here we are talking about non-expansive mapping, but the same can happen for other classes of mapping. If every bounded closed convex subset T, K to K, and any map and non-expansive mapping has a fixed point. So we say that the space has the fixed point property for these mappings. Uniformly convex, uniformly smooth, and reflexive Banach spaces with normal structure has already been sorted. So where is the problem? If we look at the non-reflexive spaces like C0, L1, capital L1, then we find that the question was that the existence of fixed point was not there. So so actually what was happening, if we look at the uniformly convex Banach spaces, they have reflexiveness. In the other case, when in the Kirk's case, the reflexivity was needed initially for and with normal structure. So now we would like to know whether if a Banach space has the fixed point property, the space needs to be reflexive or not. We can ask the same question, if the Banach space is reflexive, whether it does have a fixed point property. Both the question have the answer in negative. In 2008, a mathematician Lin obtained a result, and he showed that yes, we can have fixed point property in non-reflexive spaces. Only thing is that we need to renorm it. So it has a standard norm. Now you are renorming it with the equivalent norm, and we can guarantee the existence of fixed point. So he made a hope for the people whether non-expansive, non-reflexive spaces can have the fixed point property or not. But then the problem subsequently, Benowitz proved that a renorming of some non-separable Banach spaces with fixed point theory can be, means he proved that if we have a reflexive space, we can renorm and guarantee. But still there are two questions. Which type of non-reflexive Banach spaces can be renormed to have FPP? Is there any renorming of C0? Actually, L1 is the space where we have summable sequences. So we can see that these sequences converging to 0. But there is a bigger space where sequences does converge to 0, but the series formed by them may not need not to converge. So whether the same approach can be applied to C0 or not, that problem is still open. All these problems, these I have listed 4. There are, I have listed the main problems, but you know that there are some small problem linked to them also exist therein. And these all problems are also there for the classes we studied. So we are now studying the renorming of the spaces and whether the fixed points can be guaranteed for these spaces or not. This is all I wanted to present. Let me do some acknowledgements. First of all, I would like to thank the UJ management and Professor Mafua, for the Vice Chancellor representative, for being here, and Professor Motiti, the Executive Dean, Faculty of Science, Professor Abbas, who is the respondent for my inaugural address, Professor Nebaja, the HOD of the Department of Mathematics and Applied Mathematics, my fellow colleagues from the Department of Mathematics. I also would like to acknowledge some people. I feel that I am at UJ probably because of the lady, our ex-HOD, Dr. Wilmarie Morton. She is not here, but she has been very helpful to me. I also would like to thank Professor Goswami. I also had a discussion with him when I was preparing this talk. I extend thanks to my friends present here. Lastly, I would like to acknowledge my family, because without the family, working for mathematician becomes very difficult. My wife, Dibya, she recently completed PhD from this great University of Johannesburg and doing a postdoc here. My daughter, Ayushi, who is in grade 10 at Parktown High School for Girls. My son, Ayushman, who is in Parkview Senior School. And thank you, everyone.
Good evening, everyone. Am I audible? Good evening. Good evening. Good evening. Good evening, everyone around. Indeed, it is a very good evening for family, friends, and colleagues of Dr. Pant. I would really like to congratulate university management, especially head of department, representative of worthy Vice Chancellor, Executive Dean, for organizing this very important event and giving recognition to the contribution of Dr. Pant research. I would like to thank Dr. Pant for his insightful and thoroughly engaging inaugural lecture on approximating solution of nonlinear functional equations in infinite dimensional spaces. This lecture is indeed a pivotal moment in academic tradition and personal scholarly journey. These lectures not only celebrate an individual's scholarly achievements, but also provide a window into the evolving landscape of their disciplines. They inspire both the institution's community and the broader academic recipient by highlighting novel directions and nurturing a spirit of inquiry and collaborations. I must admit that this lecture has successfully achieved these goals by presenting both foundational insights and innovative frontiers of fixed point theory. It is affirming its wide scope and profound impact. This lecture provided a rich overview of fixed point theory, beginning from classical foundational result to the latest advancements and applications. One of the key strengths of this lecture lies in its clear and well-organized expositions. Starting with flexible motivational examples such as mirror analogy and beauty filters. The lecture then smoothly transitioned to formal definitions and seminar results like Brouwer's, Schauder's, and Kakutani fixed point theorems. The incorporation of real-world applications from economics, physics, and game theory, especially the detailed explanation of Nash equilibrium and the battle of the sexes game, was particularly notable and amazing as it connected abstract mathematics to concrete phenomena. Without any doubt, this lecture covered the breadth of fixed point theory, including matrix space contractions, quasi contractions, Suzuki contractions, and generalized quasi contraction, showcasing the progressive generalization of Banach contractions principle. The illustrative treatment of iterated function systems and fractals, such as Gauss curve and Sierpinski triangle, was an elegant demonstration of fixed point in geometric context. Furthermore, the recent developments in fixed points of non-expensive and generalized non-expensive mappings in Banach spaces were really very insightful, highlighting important contribution to nonlinear analysis. Regarding the application of fixed point theory discussed in this lecture, it comprehensively covered economic equilibria, especially Nash equilibrium as a fixed points, physical steady state heat equations interpreted as a fixed points of integral operators, constructions of fractals, fractal sets via Hutchinsonian Barnsley operators, nonlinear problems in infinite dimensional spaces. These were really a very wonderful sort of pictures which really shows how the fixed point theory is applicable to different disciplines. However, There are several additional important applications of fixed points theory which could really enrich future talks. For example, applications in differential equations and dynamical systems where fixed point characterize equilibrium states and their stability. Use in optimization theory where fixed point iterations implement projection algorithms and proximal mappings. More extensive applications in computer science, particularly in semantic of programming languages and domain theory. Role in mathematical biology. Here I would like to draw the attention of HOD, Professor Nyabda, such as a population models, because he works very actively in epidemiological models. So that is why I was asking for his attention to this part of the fixed point theory, where it has got several applications in epidemiological models and in epidemiological diseases. So it has a very significant role in mathematical biology, such as population models and epidemiology, where nonlinear fixed point methods yield existence and stability results in disease equilibria. Split feasibility problems, which help in modeling inverse problems which arise from phase retrieval and medical image reconstructions. Variational inequality problems, which are really helpful in finding time-dependent traffic equilibria. Equilibrium point problems, complementarity problems, saddle point problems, scalar and vector minimization problems, which are very actively being used in machine learning these days. So there is a long list of problems which fall into the category of fixed point theory. So finally, thank you once again for this exemplary intellectual contributions and for advancing our understanding of nonlinear function analysis. Looking ahead, it would be insightful to see further exploration of these fixed point methods applied to dynamical systems, stability, optimization algorithms involving proximal mappings and computational framework in machine learning and mathematical biologies. These are the areas where fixed point govern equilibria and convergence properties. In summary, in my conclusion, this lecture brilliantly captured the depth and vitality of fixed point theory as an essential tool across mathematics and its applications. The comprehensive survey, combined with thoughtful open problems and future directions, makes it an inspiring and valuable contribution for both established researchers and emerging researchers. Thank you. Thank you very much.
Thank you very much, Professor Pant. Immediately when I saw the title, Nonlinear Equations, I knew that we are in for a ride because linear ones are simple and straightforward. They have a changing rate that is stabilized, so to speak, versus non-linear equations. They really become abstract, and I could feel their abstractness. And then I tried to check on ChatGPT, and he said, and I choose to use the male pronoun. He said, "Are you trying to get statistical on me, brah? Are you having an exam, or are you just geeking on statistics?" Yeah, this was such an interesting lecture, and for me personally, as an epidemiologist who is involved in some epidemiological modeling work and the applicability thereof, there's a lot to learn. Thank you so much for showcasing your expertise tonight. This was about this evening. Colleagues, shall we give him a big round of applause? Shall now go and enjoy ourselves and have some nice refreshments. Thank you so much.